Welcome back, Contemporary Math. We are in Chapter 2B. This is extending unit analysis. So we are continuing to do some unit analysis in this section. So the first thing we're going to look at is the U.S. customary system. So the U.S., for some reason, likes to be different from the rest of the world. And we have our own system. And so this shows you various measurements and metrics within the U.S. customary system. And I will say this chart is also in your book. So if this is a little bit hard to read, there is a chart in your book. It's a really big chart. Got a lot of information in it. So I guess it should go without saying, but I guess it should. Well, it shouldn't. Nothing should go out without saying. But we should state that, or I'm going to state that, like, I don't expect you to memorize any of this. So if we're going to do conversions, I'm going to give you the conversion rates. I'm not expecting any sort of memorization at all. The U.S. customary system is really like horrible to memorize. Yeah, I would not do that to you. Math is not about memorizing stuff. It is about learning and the approach that you take to figuring things out, to problem solving. So I'm more interested in how you problem solve than in like memorizing stuff. That would be ridiculous to make you memorize that. So let's look at example 1. It is recommended that a patient receives 3 grams of medication. The medication is measured in grams. How many grams of medication should you give your patient? So just to recap, we want to go from gram to gram. So if I'm being honest, this might be a problem that only exists in math class. I don't really know what sort of measurements the apothecary. So medicine is known as apothecary. So if we look over here at apothecary, this is what we're talking about. It's a little bit hard to read, but it says 1 gram is 3 scruples. So I see grams here. 1 apothecary ounce is 8 grams. 1 scruple is 20 grains. 1 grain is grams. So I'm looking here. There's one thing with grams in it that I can see. And so I don't want to go from grams to grams. So it says was 0.0048. Oh, sorry, that's 0.0648 grams is 1 grain. And I see there's one thing with grains on it, one other thing with grains on it, which is this one, which is 20 grains is 1 scruple. And then the other thing, I see 1 gram is 3 scruples. So I think we're gonna have to use those 3 things. But let's do our unit analysis. And when we start out with unit analysis, we're going to start out with 3 grams. So we need 3 grams of medicine. We want to convert this to grams. So the first thing I need is something to simplify out my grams. So the conversion factor I see up here with grams is 1 gram is equal to 3 scruples. I think the first thing we're going to do is 1 gram to 3 scruples. Now we're in scruples. We want something to get rid of the scruple. Got a lot of room here. I gotta write some more stuff. Bring in some more paper. Bring in the reinforcements. So the next thing I'm looking at is things with scruples. So I just use this one of scruples, so I'm probably not going to use that again. So let's go from scruples to grains. So 1 scruple is 20 grains. And now it looks like I'm going to be measuring in grains. Zoom out. I think there's one other thing I have to do to get to grams. I'm going from grains to grams, I believe. simplify out that grains on top, I have to put grains on the bottom. And I have to put grams. In my conversion factory here, there are 0.0648 grams in a grain. 48 every one. And if I'm looking along here, I start out with 3 grams over here. If you want, and I didn't do it, but there is a 1 on bottom there if you want. This grams is going to be in the numerator, is an important thing to remember. So we're simplifying grams, circles, grams. I should end up with grams if I multiply all these things through. So I'm multiplying 3 by 20 by that 0.0648. And that should give me 11.664. And I am in grams. 11. So that is a pretty involved problem. It has 3 different conversion factors we have to do. So this next one, a friend requests that you bring 5 gallons of iced tea for a party you have planned. The tea maker you have measures tea in quarts. How many quarts of tea would you need to fulfill your friend's request? So they want us to bring gallons, and we need to know it in quarts. So we're converting gallons to quarts. So if we start with 5 gallons, this is what we need. We can always put things over 1. So if I want to change this, gallons, and I believe it's up there, gallons to quarts. This is a pretty common one. You may not have to look this up if you do a lot of cooking. But there are 4 quarts in a gallon, right? That's where the prefix even comes from, I believe, the quart prefix. So what we're doing is we're going to have to make 20 quarts. Okay. I think this one is probably a little more straightforward. It's just 1 conversion. You could probably even do this without doing your unit analysis. But I highly suggest getting used to this unit analysis. You're going to have to do it. You're going to have to do it on your test. So it's going to have to be something you learn. I don't know how else to phrase it. But you might have to start learning things in this class. I know it's a drag. But that's what we're here for. It gives you a better understanding of the world around you, hopefully. And it allows you to communicate better. The International Metric System, the meter for length, kilogram. So they say kilogram. So the prefix on here is kilo. I would probably just say grams is what is the actual word we use for mass. And gram is abbreviated G. Their definition's okay. We typically use kilograms because things weigh heavier than grams. Kilograms is more common. But I want to get at the root word. And the root word here is we use meters for length. We use grams for mass. Seconds for time. So we use the same thing for time. Liters for volume. And now we have this chart. I'm going to see this is looking blurrier and blurrier as I go. So let's see if I can fix this up a little bit. It does not look like it wants to fix up. So let's go with it. So you might notice this is like 1/10 to the first is another way that you can think about it. 4.1. So 1, you can think about it 1/10. over 100 or 1 over 10 squared. There's another way to think about that. So you might notice with negative exponents, if we want to make the exponent positive, there's a little trick is you flip it over 1 and you make the exponent positive. There are a few ways to do this. So if you know another way, it might be a valid way to do this. So we're going to convert 3,659 millimeters to meters. So if we're starting with 30, I think the way I want to go with is if we look at this, millimeter says 10 to the minus third. So I'm starting out with my decimal place here. So if we're thinking about powers of 10, if we multiply something by 10 or divide something by 10, all we're doing is moving the decimal place either left or right. And so when we're multiplying by powers of 10, that's just telling us how many places to move the decimal. Okay, so if we're going from millimeters to meters, so I'm going from something that's small to big, I'm going to be dividing this thing. So this thing should get smaller. And if we look at millimeters, the prefix is here. M is 10 to the minus third. So this is telling me that it should get 3 spaces to the left to make it smaller. So 1, 2, 3. I'm going to make it 3.659 meters. Sorry, millimeters. Meters. If you want to do this through unit analysis, suppose we can do this through unit analysis. But if we start out with this in millimeters, what this is telling me is there are 10 to the minus third meters in 1 millimeter. And so essentially what I'm doing is multiplying this by 10 to the minus third. And if you multiply it by 10 to the minus third, that is the same thing as dividing by 1,000. So if we divide this by 1,000, we're going to get the same solution. So I think it might just be easier just to think about your metric system with just moving the decimal either left or right and thinking whether you're going larger or smaller. This one is a little bit different. It says how many picoseconds are in a nanosecond? Okay, so what are we doing? We are dividing nanoseconds into picoseconds. So if you think about nanoseconds being divided into picoseconds, there's probably a few ways you could do this. You could probably count the difference between the two numbers, minus what, 9 to minus 12. That might be a quick way. But if we look at this, this is 10 to the minus 9 seconds. And this is 10 to the minus 12 seconds. And so there is a property when you have base 10s. These are the same bases. When you have the same base and they are being divided, you can subtract the exponent. So what we can do is do 10 to the minus 9, and we can subtract a minus 12. So this is something that you aren't really probably expected to know, but it's an extra little thing you can do, right? I do teach this in my algebra class, so this is an algebra equivalent class, so it shouldn't be hopefully too much without your grasp. And I can explain this a little better with the exponents and subtracting. It's probably easier to do without negative exponents because I'm like throwing two things at you at once. But this is -9, and I'm going to add 12. But you might notice there is a power of 3 difference between 9 and 12. And so if it was negative, it would be 1/1000th, would mean you just have to flip it. But it's 10 to the third, this is 1,000. So there are 1,000 picoseconds in a nanosecond. And so the metric system, I can give you what was I now? I can give you whatever sort of base, right? And it really doesn't matter, to be honest, like in the grand scheme of the math, right? It really doesn't matter what base I give you in the grand scheme of the math that you're doing. When you go back to interpret it, you do have to interpret what the heck you're doing in the problem. But here is really what we need to focus on, right? What are the prefixes and how are we going? Are we going to get a larger number or are we going to get a smaller number? So if we're going from something small to something big, we're going to be dividing this thing. So we're going to get a smaller number. If we go from something big to something small, we're going to be multiplying. So small to big, divide the big, big to small, multiply all. Is the thing that I used to learn in elementary school. So it's coming from Miss Thomas in 6th grade. And so we'll do a little bit more work in class about the powers of tens and how to do those. And here's another chart that's probably blurry on your screen, but that is in your book. All these charts are in your book. And when you print them out on your paper, they're not nearly as blurry as they look on my screen. So I think they should suffice for this lesson. So how many miles is a 13-kilometer race? So now we've done, let's step back and look at what we're doing. Sorry, got a little ahead. So what we did is we went from the US system, the only we use, and maybe like 1 or 2 other places, and the metric system, which the whole rest of the world uses. And now we're going to convert between the two. So there is a conversion between the two. And I do believe the current US system is actually based off of the metric system. But that's what I read last. It could be wrong. I might have to reinforce that with some sources, but it's what I heard. So how many miles is a 13-kilometer race? So if we start with 13 kilometers. About that as being over 1. So if I'm looking at this thing, I'm looking for my kilometers to miles. I see. See on mine. 1 mile equals, there it is. Blurry as heck. But 1 mile equals 1.6093 kilometers. And I think they give us the other one over here too, right? 1 kilometer equals 0.02. So it depends how you set this thing up. You could use either one. And this is kind of like that previous table with the currency. Like they are just sort of reciprocals of each other. Whether you multiply by this or divide by this number, you're going to get the same result. And so I think I'm going to use that first one. 1 mile equals 1.6093 kilometers. 1 mile equals 1.6093 kilometers. So if I have, yeah, I'm starting with 13 and dividing by 1.6093 by kilometers, simplify out, and I would be left with 8.078 miles. And then maybe like take a step back and think of this, like, does this answer make sense to you in context of what you know about the world, right? If we start with 13 kilometers, does it make sense that it would be about 8 miles? So miles are going to be a little bit less than kilometers. So your kilometers will always be a little bit larger. So that seems to make sense. Hopefully, like intuitively, sort of like, well, not intuitively, but hopefully with what you know in context to the world, right? How many square feet are in 1 square meter? So if we look up here, where's my meters? 1 meter equals, where's my, there it is, 1 meter equals 3.28 feet. 1 foot equals 0.308 meters. So I think I'm going to go with the 1 meter equals 3.28 feet. How many square feet are in 1 square meter? So if I start out with 1 meter and I want to square it, for every 1 meter, there are 3 feet. For every 1 meter, there is 3 feet. 3.28 feet, sorry. Let's be a little more accurate. I got used to saying yards, and now we're swapping to meters. They're a little bit longer. So every 1 meter is 3.28 feet. So 1 meter squared. And if we do 3.28 times 3.28, we're going to get 0.7584 feet squared. So how many square feet are in 1 square meter? So I did it with like fractions. I guess you could have also just said 1 meter. 3.28 feet. You could have multiplied equations down to find the equivalent thing. If we multiply 1 meter by 1 meter, it's going to give us 1 meter squared, 3.28 feet by 3.28 feet. I'm essentially doing the same thing. I'm just comparing a meter to feet, a meter to feet. Seeing what happens if I multiply the things. 1 meter squared is going to be compared to 10.7584 feet squared. So there's a few ways you can do this conversion factor, but the question is asking us for this number right here. Somehow you want to box your answer to let me know that's what we're talking about. Definitely making your work cleaner makes me want to grade it a little bit more. Makes me a little happier to put some points on your paper. Okay, so we did some standard, we did some metric, we did some standard geometric, and vice versa. And now we're going to do some temperature. So there's Fahrenheit that we use mostly over here. There's Celsius that's used most other places. And then there's this thing called Kelvin that they derive to measure absolute zero, or where there is zero energy in an object. And so we want to convert one temperature to another. We can convert Fahrenheit to Celsius and Celsius to Fahrenheit with these first two. And then we can convert Kelvin to Celsius and Celsius to Kelvin. So you might notice that we don't have a formula to convert like Fahrenheit directly to Kelvin. We have to go use that middleman called Celsius if they ask us to convert between the two. So it says ethanol freezes at minus 173.5 degrees Fahrenheit. So what is the Celsius and what is the Kelvin? So what do we want to solve for? We want to solve for Celsius, we want to solve for Kelvin. I kind of said it. We're going to probably have to do this thing first. So we have a Fahrenheit. We want to convert to Celsius. So there are two formulas we see here. If I'm being honest, it's the same formula, just rearranged. So you could use either one and it should give you the result. But there is one that is sort of probably should be easier to plug into. So if we want to solve for Celsius, there is one of these formulas that is solved for Celsius. It is not this one. This one is solved for Fahrenheit. So the other one looks like C equals F minus 32 divided by 1.8. So I have to subtract 32 and then divide by 1.8 to get my Celsius. So my Fahrenheit is minus 173.5. I have to subtract 32 from that and divide by 1.8. So I'm doing minus 173.5 and I'm subtracting 32, so it should be a larger negative number. And this is why we do math in pencil. And this is divided by 1.8. And when dividing a negative by a positive, I'm hoping you realize I should be getting a, I said the wrong thing. I should be getting a negative number out of this thing. So let's look. Here, let me use some paper. Running out of room on that one. I'm getting a minus 114.16. I'm going to round that to 7. So I'm going to round it to 0.16. And converting Celsius to Kelvin and Kelvin to Celsius is just a factor of either adding 273 or subtracting 273.15. It's not a big sort of leap. But if we want to solve to Kelvin and we have our Celsius, this is the formula we're going to want to use. So we want to solve for Kelvin. We have our Celsius. Our Kelvin is equal to Celsius, which is minus 114.167. And I'm going to add 273.15 to that. And that should give you something like 158.983. That's what it is. 158.983. So these were the two things they asked for. So when you get done, be nice and put some boxes around them things. Let me know you know what you're doing. It's a little easier to follow your work then. I know where the start is usually. It's easier to find the start and the finish then. And we got two sort of like little things to cover. There are two sort of subunits left. We have done quite a bit already. Just a little bit more. So this section, we're going to talk about energy and what the difference is between the two. So energy is what makes matter move up or heat. The international metric unit of energy is the joule. So power is the rate at which energy is used. The international metric unit of power is the watt, defined as 1 watt equals 1 joule per second. Okay. A kilowatt hour is a unit of energy. So 1 kilowatt hour is 3.6 million joules. Okay, so how do we think about this? There is so much energy. So this is like how much power there is. Well, that's how much, we're using the wrong word. This is how much energy there is. It kind of says it there. I'm trying to think of an easier way to describe this without using the words they're using. So if you fill up a tank of gas in a car, I think this might be a good way to think about it. If we have 5 gallons of gas, that gas is going to have the same energy regardless of where you put it. If you have 5 gallons of gas, it's going to have the same amount of joules in that thing. So if we think about that, like that has a fixed amount of energy, but depending what car we put it on, whether we put it in like a souped up automobile or just a regular car, it's going to use it at a different, each one of those has a different power at which they use it. So this is the rate at which you're using your energy. So like a super souped up muscle car is going to use a lot of gas. It's going to use a lot of that energy per second. It's going to use a lot of gas per second, but it's going to have a lot of power. And vice versa, right? A regular car, a jalopy that you're driving out there, it's not going to use very much gas, but it's not giving you as much power as that muscle car, right? So maybe that might be a good way to sort of think about these things. This is the energy. It's like a fixed amount of stuff that's there. And this is the rate at which we're using it up. And so they come up with this kilowatt hour. And we have kilowatt hours and we're going to joules. So a watt is what? 1 joule per second. That's the way I want to think about this. Oh yeah, this is where I was going with this. 1 watt is 1 joule per second. So if I think about kilowatt hours, we talked about this, but this hyphen means kilowatt, and we're multiplying it by hours. And so it's kind of weird because this is a power measurement, this is a time measurement. But when we multiply them, we're going to get back to joules. So if we think about this, I have kilowatts times hours, but I can convert from what? Kilowatts to watts. And I don't want to do the measurement, but I know I can convert from kilowatts to watts, and I know I can convert from what? From watts to joules per second. That's a weird thing. So watts, and I can do joules per second up here. And if I do this, this is going to simplify out my kilowatts, my watts. I'm going to be left with something joules per second times hours. I know I can convert my hours to seconds. I don't want to write it too much, but hopefully this makes some sense as to why we're getting back to joules. If you multiply this times the time, you're going to get back to your joules. So you are walking on a treadmill, which reports you are burning 350 calories per hour. Are you generating enough power to light a 100-watt bulb? So 1 calorie is 4,184 joules. Okay, so they're giving us a conversion factor. So this is a lot to kind of process, but we are starting out with what you know. 350 calories per hour is what we're generating, and we want to know if that is 100 watts. So we know this is 350, and we're going calories for every 1 hour. So when you're setting up these fractions, and I hadn't done it yet, but you might actually set these up things up backwards. That's okay. Like just flip them in the end. If you're doing good work and you just set up and you end up with units on the bottom, which we might end up doing at some point, it's okay. You can just flip it. Make a mental note of it, right? So this is 350 calories for every 1 hour. And where am I going? I want to go from calories, and it's a little bit of a hint. This is the only thing we really got to relate to calories. So I want to go from calories to joules. And then there's 4184 joules for every 1 calorie. So that's the next thing I'm going to do. That is going to get rid of my calories. So if you want to mark these off as you go, you can. If not, you can wait till the end, or you can not do it at all. I think marking them off really kind of helps see where we're going, though. So I'm going to do it as we go. And now I'm multiplying this guy. I'm multiplying them by something to get rid of joules. So I have joules on top. I want to put my joules on the bottom. Wait. No. Joules is okay. think I'm going to keep my joules on it. So I want to end up with something that is in watts. And saying watts is like saying joules per second. So I want to end up with something that is in watts. But if I say watts, I think it's actually easier to do and solve for joules per second. And so if I'm looking at this, now I'm looking at this with the new lens. Knowing where you're going, like you said before, that's step one. So I guess I got a little ahead of myself and tried to jump into step two without realizing where I was going. I thought I was going to watts, which you can, but I don't want to spend an extra step with an extra conversion. Let's just go to joules per second, because that is exactly the same thing as watts. So if we're looking at this, I have joules and I have hours on the bottom. So now I want to go from hours to seconds. Hours on the bottom, I have to not drop the paper. So I have hours on the bottom, I have to put hours on top. I have to put minutes. 1 hour is 60 minutes. Minutes to seconds. Minutes. Multiplied by 4184. Which is going to give me a rather large number. 146.0. And I'm dividing that by 60 times 60, which is 3,600. Yeah, I got joules per second. And I want to divide these two numbers. And I should be getting something like 406 point, I'm going to round it to, I guess, two decimal places, 78. And this is in joules per second, which is the same thing as saying it's in 406.78 watts. And so is this enough to run a 100 kilowatt bulb? Yes, 4 of them. Right. You could run 400 watts. You have 6 watts left over. Okay. So this one was pretty involved. But we should be able to do it with some unit analysis. And knowing where you're going before you start heading there is definitely an advantage. Step one before step two. And the next thing, we have an electricity bill. So the utility company charges 12.5 cents per kilowatt hour of electricity. How much does it cost to keep a 75-watt light bulb on for a week? How much would you save in a year if you replaced the bulb with an LED bulb that requires 15 watts? So they are asking quite a bit in this question. So let's break it down first. First thing we want to figure out, and the first thing they kind of ask is about a 75-watt light bulb for a week. And we know they charge per kilowatt hour. So we have a watt by a week, and we want to convert that to kilowatt by hour. 75 watts. And you might need to pull out some more paper. I probably did not leave you enough space for this one. This one's a pretty involved problem. So we're going to go with 75 watts, and we're going to go 1 week. I'm going to jump to 7 days, if that's fair enough. So we're going 75 watts for 1 week, which is 7 days. We're multiplying those things together. We want to get to kilowatts times hours. So if you want, you can put this over 1. We're multiplying this, and we want to go from watts, kilowatts. And in order to do that, there are 1,000 watts in 1 kilowatt. And so this is going to get us our kilowatts we want. We have 7 days, so we need to go from days to hours. So we want to simplify this days. So this is days on bottom, hours on top. There are 24 hours in 1 day. And we have a few things to multiply and one thing to divide. We're going to go 75 times 7 times 24. 75 times 7 times 24. That gives me 12,600. And then I want to divide that by 1,000. So this should be giving me something like 12.6. And just to recap what we're in, we got rid of the days. That should be marked off. We are in kilowatt hours here. So we are in kilowatt dash hour. So we got 12.6 kilowatt hours to run this thing for a week. The next thing we want to know is the cost. So if we have 12.6 kilowatt hours, and the company charges how much? 12.5 cents. So 0.125 cents for every 1 kilowatt hour is what they're telling me. How much is that going to cost? And this is probably easy enough to where you don't have to figure it with the unit analysis, right? But we can set it up with the unit analysis. We can figure out, hey, we're simplifying out our kilowatt hours. And we're going to end up with a price that is 1.575. So I'm going to round up. It's probably going to be $1.58. I think that might be the first question they ask. Utility reread it. So your utility company charges that much. How much does it cost to keep a 75 watt bulb for a week? There you go. That's for a week. How much would you save in a year if you replace the bulb with an LED bulb that is 15 watts? So I did this work. And this is per week. And so we can do this a few different ways, but I think the first thing that I want to do is figure out, I have this one in a per week rate. I want to figure out this one in a per week rate, and it would be very similar to this problem. I'm going to do everything the same. I'm going to figure out what does it cost to run this thing for 7 days. So everything should be the same except for this number. So hopefully you realize, and you can save yourself maybe a little bit of time. I'm going to do 15. I'm going to multiply that by 7. I'm going to multiply that by 24. And divide by 1,000 is the process that I want to go through to figure out what this thing runs per week. So I'm going 15 by 7 by 24. It's giving me 2520. I'm going to divide that by 1,000. This is giving me 2.52, and this was in kilowatt hours. So this should be mimicking this thing that we found earlier. And I know this is 2.52 kilowatt hours. The next thing I need to do is multiply that by the 12.5 cents. And if I do 2.52, and I multiply that by 0.125, I should be getting 0.315. And this is the dollars, and so we're going to round this to 0.32. So I think we even rounded the other one up from 0.5. So they should be even with the rounding. Okay, and this is per week. So we could either convert these to annual rates now, or we could just look at them. We have this one is costing us 32 cents. This is costing us $1.58. So the difference between $1.58 and what, 32 cents. That's gonna give me 1.58 minus 32 cents is $1.26. So each week we're gonna save this per week. If I want to know per year, there are 52 weeks in a year, so 52 times 1.26 should be giving me 65.52. So that's a little decent chunk of change that you might save if you replace it. It might convince you to buy something with a lower wattage, right? It might be worth this, even though the bulbs might be more, it might be worth the savings in the long run. But that's also assuming you're going to stay in your place for a minute, all right? Buy some cheap bulbs when you move out. That's the strategy. So that is problem example 8. The last thing we're going to talk about on this paper is units of density and concentration. So there are very select things that we're going to talk about sort of with density and concentration. So they say here density describes compactness or crowding is how they're defining this. So there are a few things they want to talk about density with. One of the things the book talks about density with is material density. So think about things that we refer to density with. Material density is one of them. And this is mass per unit volume. So mass is like how much material can we fit in a certain volume or of space. And the unit that they use for this is grams per centimeter cube. So like a heavy metal would be more grams per centimeter cube than like some feathers or something like that, perhaps. So we can think about, like heavy metal versus feathers, that would be like material density. And so the metal would be more dense, it would be heavier. And so with this, the density of water, we want to talk material density of water, is 1 gram per centimeter cube. And so when we talk about buoyancy, things that are less are going to float. Things that are more will sink. There are 2 other things that they talk about density with in the book. And if we want to talk about cities, one thing you might pop up, or might pop in your mind, is population density. How many people are living in a square foot? So number of people per unit area. So number of people per square mile is one way that they do it, unit area. Probably people per square kilometer if you're overseas. And the last thing we want to talk about is if we talk about technology and the space on a chip, that would be the information density. So we're talking about memory storage on digital media. So they go 1 gigabyte per square inch is what they're doing. Okay. And so these are going to be the sort of like 3 different things that we talk about with respect to density. And so we're talking about density describes compactness or crowding. The other thing is sort of similar. It is concentration. And so we're still talking about like how much of one thing is in another. So how much of one substance is mixed in with another. And so they give us sort of three things that they look at in the book. Concentration of air pollution, spell air pollutant. And when we talk about concentration of air pollutant, we talk about this measurement called parts per million, or ppm is one way to think about it or say it. And so what are we talking about, parts per million? And so what they're actually talking about are the actual little individual molecules of these things. There are so many molecules per million molecules in the air of a certain thing. So if we're talking about certain carbon pollutants, there are certain, that tells you how many carbon molecules are in the air per million molecules. The other thing is medicinal dosages, or medicine dosages. Are often based on concentration. So the concentration is based on your body weight. And so they will give them in milligram per kilogram. And what they're talking about here is this is the milligrams of medicine per the kilogram of the person's body weight. And the last thing they talk about is blood alcohol content. So I'm going to abbreviate BAC. I think most of us know the abbreviation here. And what they do is grams to milliliters. So they do grams of alcohol. So how many grams of alcohol are in your blood to the milliliters of blood that are in your body? And the legal limit is what, 0.08 grams for every 100 milliliters. Okay. One more page, just a few more problems to go. Austin has a population of 9,000. This is probably a few years ago. I think it's grown a little bit since then. Austin has a population of 947,890 people living in an area of about 271.8 miles squared. And that's the kilometers squared. So what is the population density? So if we want to know population density, we're going to take people, 947,890 people, and we want to know this per, which says division. So when I hear that word per, I'm thinking divide per square mile. So Austin is 271.8 square miles. So if I'm looking at this here, 947,890 divided by 271.8 should be giving me 3487.45 people per square mile. Did I do that? That is, let's see, 947. Let's double check this. Divided by 271.8. That is correct. That is rounded down a little bit, actually. 0.4 there. And so we should probably round it to the nearest person. 3487 people per square mile. If you do the square kilometers, you should get something like 1346.151, or about 1347 people per square kilometer. Okay. Now we have a dosage problem. So a child weighing 45 kilograms has a bacterial infection, which is to be treated with amoxicillin at a dosage based on 25 milligrams per kilogram of body weight per day, divided into doses every 8 hours. So how much amoxicillin should the child be prescribed every 8 hours? Okay, so if we have 45 kilogram child, and we know the medicine dosage is 25 milligrams to kilograms. So you may not set this up correctly. You might accidentally flip things, but if you know you have a whole number, you can always put that over 1. And if we want to get rid of kilograms, kilograms is going to go here. Milligrams is going to go here. So I know 25 milligrams for every 1 kilogram. So what I'm doing is 45 times 25 is going to give me 1125 milligrams. So this is the dosage that is recommended for the child per day. So this is how much he's getting every day. He's getting 1125. This is not how much you want to give him at one time. If you do that, you will absolutely probably kill this kid. Maybe not with amoxicillin, but with anything else, there's a good chance he might be poisoning this kid, right? So we want to know the 8-hour dosage. There's a few ways to think about it, but we're dosing him every 8 hours. We're going to give him 3 doses. 3 doses should add up to this. I'm going to divide this by 3. You might figure out that is 3. Per day. Okay. Now we know the dosage for every 8 hours. It's 375 milligrams. Now the next question asks, if the medicine is to be taken with a liquid suspension that has a concentration of 10 milligrams per milliliter, how much should the child take every 8 hours? So now your medicine is actually coming in milliliters. You have to measure out milliliters of medicine. So we know we need a 375 milligram dosage. We know we want to simplify out the milliliters. Divide that by 1. Of the suspension. Okay. So now we are looking at the last problem here. This is a bit of a silly problem, probably. But it says an average man has 5 liters of blood, but this weirdo Bildar has a whopping 8 liters of blood. And an average 12-ounce can of beer contains about 16 grams of alcohol. But Bildar is a weirdo. When he drinks alcohol, all the alcohol is immediately absorbed straight into his blood. How many beers can Bildar consume before he is legally intoxicated with a blood alcohol content of 0.08? Okay, so we start out with a 12-ounce can of beer. So 1 can would give you what? 15 grams of alcohol. If he consumes this, he's going to consume it, and it's going to be 15 grams. And his liters of blood is 8 liters. So if we go 8 liters, he's going to have 15 grams and 8 liters of blood. His body absorbs it immediately. It's kind of silly. It's not the way your body works, but that's the way we're going here. let's go with it. So we want to go from liters to milliliters. Liters to milliliters. And I want to set it up so that my liters simplify out. So 1 liter is 1,000 milliliters. So you might notice he's getting 15 grams for 8,000 milliliters. And this is giving 0.001875 if I throw it into a calculator. This is what I'm going to get. And this is a measurement in grams per milliliter. Per milliliter. I'm running out of room here. Oh, there we go. Okay, so it's a little bit of a weird thing, but we need to know grams per 100 milliliters. So if we have 0.001875 and we have grams for every 1 milliliter, in order to get to 100 milliliters, we have to multiply by 100 there. We'd have to do the same here. So we're moving this thing 2 decimal places, 0.1875 grams for every 100 milliliters. So the legal limit is 0.08, and this thing asks how many beers can he consume before he's legally intoxicated. Well, after one can, he has a 0.1875 gram per milliliter. He's already over the limit at 1 beer, way over limit, over twice the limit. So he cannot even drink 1 and go. So I guess this is the drawback of being an alien being with a gun head. But that is the end of this section. We will get some more practice on these unit conversions. So we have 2 sections over unit conversions, and then the next week we will be going over chapter 3 stuff, which is all about, the first 2 sections are about percentages, and the other one's about putting numbers into perspective, I believe. So we will go over that and be doing probably some more unit analysis, to be honest. I believe it is also involved in that section. So you're going to have to learn unit analysis. I don't believe there's any way around it in this class. If you have questions, you can come see me during office hours, but you're going to have to learn this stuff. And it's going to require you doing some work on your own and trying things before I do them. So good luck and study hard.